continuing the theme of ruining enzyme activity, just messing up enzymes' days. We're out of inhibitors, and now we're going to talk about the fact that enzyme activity is heavily influenced by the conditions enzymes are in. So it's important to remember that enzymes are the product of a living thing, and living things are products of their environment. In other words, living things evolve or adapt to their environment, right? And that means that the enzymes that they produced are also adapted to their environment. So whatever that environment may be, if it's an enzyme in your stomach, your gastric cavity, stomach acid is pH 2. So enzymes that have to be active in stomach acid would be adapted to being active in pH 2. So this is pretty simple here. So enzymes are adapted to their environment. And what that means is that just like a tropical lizard has an optimum environment with regards to something like temperature and humidity, enzymes all have optimum environments, right? So we can think about optimum environment as the environment that enzymes are adapted to. And this would include factors like pH, temperature, right? Humidity could be one of them. You could have osmolarity be one of them. Salt content, so salinity. Lots of things can represent the environment. So when we talk about enzyme activity is best or highest in optimum conditions. So if the enzyme is adapted to the pH 2 of the gastric cavity, then its activity will be best at pH 2. Enzyme activity is highest in optimum conditions. And the corollary to that, of course, is that enzyme activity, so enzyme activity decreases as you get further from optimum conditions. And this creates a situation where you have not just an optimum environment, but an environment that could be described as an optimum range. So, yeasts generally do best at 28 to 32 degrees Celsius when it comes to optimum environment for yeast functioning. So the enzymes in yeast are operating at peak activity 28 to 32. So yeast, optimum temperature, range. 28 to 32 degrees. Now, as you get further from that, enzyme activity will start to decrease. I like to use blood. So you don't need to know the term the enzyme carbonic anhydrase, but it's an important enzyme in the blood that manages carbon dioxide levels and manages carbonic acid levels in the blood. So that's an example of a really important blood enzyme. There's a lot of very important blood enzymes, including a number of enzymes associated with like the clotting cascade. Or enzymes associated with immune functions. There's a lot of important enzymatic activity happening in the blood. And let's talk about human blood enzymes with regards to optimum ranges. So, human blood has a pH of 7.4. This is very tightly controlled through homeostasis, which means that your optimum range is actually going to be a very small range around that. Probably like 0.05. Don't quote me on that. But it's a very small optimum. So this is my optimum range. Enzyme activity is at its highest there. As we get further from the optimum, enzyme activity decreases. Why does enzyme activity decrease as you get further from the optimum? And that is all about conformation. Once again, conformation. So, the three-dimensional structure of an enzyme is especially important because the active site, its ability to actually catalyze the reaction from its substrate, is determined by its active site. So, we'll just use a little square. And here's my enzyme with its peak active site. You know what? I'll make that bigger too. So there we go. Enzyme with peak active site. Now, as we move away from optimum, we start to have conformational changes. The enzyme conformation is altered. It begins to lose conformation. So, as we move away from optimum conditions, we have alterations to the enzyme's structure. It starts to lose conformation. So, as you move further and further, conformation starts to get more and more affected. So, maybe slightly outside the optimum, it's minor. I'll put a slight curve in there. There you go. But the further you get, the more that alteration starts to hit. So, let me be pedantic. Right? So, we have our substrate molecule here, and we can see nice high specificity there. But with this alteration, it's not quite as the affinity has decreased. As the active site changes, the affinity decreases. And so there's a greater chance that it won't create a bind tight enough to catalyze the reaction. And the greater that active site is altered, the lower affinity it has, the more of its conformation is affected, and it can get pretty bad. Right? But as long as you're not too far outside the optimum, this is reversible. Homeostasis exists for a reason. So if your blood pH, let's make this side here alkaline. So here's 7.8, which is our death point, and here's 7.0, which is our death point. So if you're getting outside there, but you get to the hospital and you get some dialysis or something, so your blood pH is going up. Oh no! But then you go to the hospital, you get some dialysis, and it goes back down to 7.4. Well, the good news is all these alterations, right, they are reversible. So as long as you don't get too far outside, these conformational changes are reversible. They're just a product of chemistry, right? The enzyme folds up correctly and compacts into this ribbon correctly because of all of the chemical bonds it forms and all the hydrogen bonds and disulfide bridges it makes in its optimum conditions. And if you're outside those optimum conditions, some of those bridges and bonds start to sort of unwind a little bit, and you get those active site alterations. But they're all just contingent on optimum, so as you go back towards optimum, it'll reform. But there's an exception here, and that's when you get too far, right? If you get too far from the optimum, you will have an irreversible loss of conformation. So there is a point, a threshold at which your conformational changes have become irreversible. What a world, what a world. And now your enzyme is an X enzyme, right? So this right here is an irreversible loss of conformation. And the vocab for an irreversible loss of conformation is denaturation. So, denaturation is the irreversible loss of conformation when you get too far outside the optimum for any macromolecule. So, an enzyme has a denaturing point. And as long as you don't exceed that, those alterations due to being outside the environment are reversible. But once you pass the denaturation threshold, the denaturing point, the enzyme becomes denatured. It denatures, it loses its irreversibly loses its conformation. It has become denatured. Right? Denaturation is the process of losing conformation irreversibly. Denaturing is you are currently losing your conformation irreversibly. So, this is just grammar at this point. But denature is pretty important vocab. And for any conceivable condition, pH, temperature, all of that, there's denaturation points. So it's important to note that this is a particularly drastic way you can lose enzyme function. So, and that is the end of how to absolutely wreck an enzymes day. So we'll move on to regulating enzymes in the next video. Au revoir.